Hello students and welcome to another lecture. Today we are going to cover chapter 8 of the course Digital Logic Design. This chapter is about the counters and the counters design. So let's begin. So let's first start with a brief introduction of counting in binary. We have already discussed counting in binary in our initial chapters. That is the number increases by 1. So it's like if it's a 3-bit number, it starts with 000, then it 001, 010 and so on. Also, if you remember, we discussed about a pattern in counting, that is the least significant bit changes every number. So and the second significant bit changes after every 2 numbers. So you can see the pattern here. Similarly, the third number would change after every 4 numbers. And similarly, if there is a fourth bit, then it would change after 8 numbers. So it's always 2 raised to power n, where n is the position of the bit counting from the start. This would make our life easier to design a counter, because now we know the pattern, so we can design a counter using flip-flops, as we have seen before. Since we have seen that flip-flops could be used as frequency dividers, so the only thing that we need to do is that we could use one flip-flop to divide the frequency in half, so that every second flip-flop, every other flip-flop would divide the frequency in half. That would in turn change the numbers of the bits from 0 to 1 or 1 to 0 after a certain number of bits, depending upon its position. So this is also, you can see it from these waveforms. So the least significant bit, it looks like a clock. It changes with every clock. So it's 0 1 0 1 and so on. The second bit changes after every 2 numbers. So it's 0 0 1 1 0 0 1 1 and 0. So if you compare these first two waveforms, the second waveform also looks like a clock, which is changing at half the frequency of the least significant bit. Similarly, the third bit, the frequency is further halved, and every next bit, every subsequent bit would change its frequency in half. So that means we can use flip-flops in cascade, one after the other. And if you remember, we have said that flip-flops, for such matter as a frequency divider, could only be used if they are in the toggle mode. So that means we can have flip-flops, either a JK flip-flop or a D flip-flop, as we have seen yesterday in our lecture, where all its inputs, JK or D for that matter, are active high, or they are always high. And in case of a D flip-flop, the Q bar output is connected to the D input, so that at each stage every flip-flop is in the toggle mode, so they would change the frequency of half the frequency of the output. Here we can see such assembly. We have 3 flip-flops, and this assembly could be used as this cascading of flip-flops could be used as a 3-bit counter. You can see the J0, J1, J2, K0, K1 and K2, all of these inputs are connected to continuously a constant high input. The first clock is directly driven by a clock signal. The second clock is then driven by the Q0 bar output of the first flip-flop. Similarly, Q1 bar output of the second flip-flop. So if we look at this, if we analyze it, you can always see that with each clock input, with each clock pulse at the input, the first flip-flop output would change with every rising edge of the clock, or trailing edge for that matter. The second flip-flop output would change after 2 edges, or after 2 clock pulses. The third flip-flop output would change after 4 clock pulses, and so on. So we can also see that in the waveforms. This is Q0, which changes with each clock pulse. Q1 changes with each 2 clock pulses, Q2 changes with each 4 clock pulses, and so on. These are the flip-flops that we are considering, the counters that we are considering up till now are considered as asynchronous counters, since their clocks are not synchronized. Each flip-flop is driven by the output of the previous flip-flop and not by a direct clock. So that's why they are called asynchronous counter. The problem with asynchronous counter counters is that they have a propagation delay. We have seen in the previous lecture that there is a certain amount of delay, probably in nanoseconds or milliseconds, between the clock input and the time when the output can be achieved. But since each subsequent flip-flop is driven by the output of the previous flip-flop, so this delay is added. So for example, the first flip-flop, if it has a certain delay, as you can see in this waveform, the second flip-flop would have 2 times the delay because it is added upon the delay of the first flip-flop. Similarly, the third one has a 4 times more delay. So the propagation delay increases with each subsequent flip-flop. And for that matter, if we want this assembly of flip-flops to work as a counter, we would like to minimize the delay, or we would like to increase the speed of the clock such that through a number of bits, the total propagation does not increase, the time is not larger than the time period of the clock, so that the 2 pulses of the clock are not mixed together. This is a major disadvantage of an asynchronous counter, but we can also have a synchronous counter, which you would see in the subsequent slides, where we would avoid this propagation delay problem. Okay, so this is an example of a decade counter. A decade counter is a counter which could only count from 0000 till 1010, or from 0 to 9, right? So that is, it should be reset after it reaches the number 9. So for that purpose we use a decoder kind of structure, like here as you can see it. You can also call it a BCD counter because it counts only the numbers that are in the BCD sequence. And the remaining sequences are truncated. The main method to implement this is that whenever it reaches the final number, that is 1001, which is the binary for 9, it should reset to 000 instead of going to 1010 or 10. So that is why we have connected these 2 outputs, Q1 and Q3, which is 1010, the 2 bits that becomes 1 at 1010, and they are passed through a NAND gate, which would produce a 0, and that 0 is used to clear the outputs of all the flip-flops. So all the flip-flop output would become 0000, while without this it should have been 1010, and after that the counter would reset and it would again start counting from 0000, then 0001, and so on. We can obtain any truncated sequence based on this approach. For example, if let's say if you want to use this 4-bit counter to count from 0 to 11, then you'd have to reset after you reach the binary equivalent of the number 11, and so on. And so you can again use an AND gate, you can get the inputs from all the outputs where the output is high or 1, such that this produces a low output or 0 output, which would clear all the inputs and clear all the outputs as well. We can also see this from the waveforms. This method of truncating is called a glitch. That is whenever the Q1 and Q3 reaches, when for the first time they both reach their high level, which is in case of 1010, the counter would reset because it would activate this clear signal momentarily. It would make it low, and then the counter would reset to start counting again from 0000. We can also make an asynchronous counter using D flip-flop. The only thing that we need to do is, since D flip-flop could be made into toggle mode if we connect the Q bar output to the D input, so it would always remain in the toggle mode. So these are some waveforms. We have a clock, we have LSB, MSB, and clear signal, which could be used to reset the flip-flop to a truncated level of counter. So for example, this counter would count sequence like 0 to 1, then clear, and then repeat. Here is an example of an IC which is called 74LS93A, which implements an asynchronous counter. It has two clocks, clock A, which is connected to a flip-flop, and another independent clock B, which is connected to the second flip-flop. With clock B, it implements a 3-bit counter, and but we can actually connect the Q0 output to the clock B to make it into a 4-bit counter. And then we have two more extra inputs, R01 and R02, for the reset purpose. Another type of counter is synchronous counters. The synchronous counters, as the name suggests, the clocks to every flip-flop are in sync, or all the flip-flops are driven by the same clock. So now there is a bit change in the assembly of how the inputs are driving the outputs. So for example, now each input, each J and K, they are both would get the same input, but now the input is not constantly high, but the inputs are coming from the output of the previous flip-flop. So for example, the second flip-flop receives Q0 as input to both J1 and K1. The third flip-flop would receive the AND between Q0 and Q1 as input. There is a fourth flip-flop. If it's a 4-bit counter, it will receive Q0, Q1 and Q2, all three as inputs. So with each for each flip-flop, the inputs are basically the AND operation between all previous outputs. We can also very easily analyze them and see that this would actually work as a legitimate counter, counting from 0000 up till 1111 and so on. So here is some analysis of the outputs. We have Q2, Q1 and Q0 for a 3-bit synchronous counter. J2 is equal to Q0, Q1, the AND between the previous two outputs. K2 is also the same. J1 is Q0, the AND operation, or just the previous output, because this is just single output. K1 is also equal to Q0. J0 and K0 are both constantly high. So with this, you can easily determine that J1 and K1 would be 0 in the beginning, because Q0 is 0, it's the first output. J0 and K1 are constantly high, so they will always remain 1. Similarly for the next bit, since now J1 and K1 are 0 and J0 and K0 are 1, so now the next output would be 0, 0, 1, since the output of the third flip-flop would be equal to 1, and the output of the first two flip-flops would still remain 0 because the inputs are 0. We can also determine the subsequent inputs and outputs in this manner. So in the next stage, the J1 and K1 also becomes 1, and in the next stage the output is 0, 1, 0, and similarly you can see that the inputs are changing. So for, let's say, in the fourth row, all the inputs are 1, so all the flip-flops are now in the toggle mode. And you can see here that the counter would reset at after 111, it would reset to 000. Okay, let's look at a 4-bit synchronous binary counter. As you can see, now we have 4-bit counters, so we have 4 flip-flops. The input of each, the two inputs J and K of each flip-flop is driven by the output of the previous flip-flop through an AND gate. So for example, the first flip-flop is receiving directly a high input all the time. The second flip-flop receives Q0 as the input for both J1 and K1 inputs. The third flip-flop receives input at J2 and K2 as the AND between Q1 and Q0. The fourth flip-flop receives input at J3 and K3 as the AND between Q1, Q0 and Q2. So this is how a synchronous counter would go on. For example, there could be more flip-flops So which would make like we can make a 5-bit counter or a 6-bit counter accordingly. You can also look at the wave diagrams. So we can see there is a clock at a certain frequency. The Q0 has frequency half of the clock. Q1 has frequency 1/4 of the clock. The Q2 has frequency 1/8 of the clock, and so on. We can also make a BCD decade counter from in terms of a synchronous counter. So in that case we have to reset the counter after 1001, so such that the counter recycles to 0000, and there is this assembly at here which works as a decoder, which receives, instead of getting the AND between Q0, Q1 and Q2 and Q3, it actually AND Q0 and Q3 and Q1 and Q2, and then OR them together, which would reset the flip-flop after it reaches 1001 to 0000. You can also see that from the waveforms that once the flip-flop reaches 1001, as you can see at the 9th clock pulse, it would reset to 0000. These same waveforms can be obtained with an asynchronous counter in IC form, which is 74LS90, which is available in dual version of the 74LS390, which can be cascaded as well. The problem with the asynchronous counter is that it's slower than the synchronous counter with a maximum count frequency of 35 megahertz, but it's simpler because we do not need to have so many AND gates and attach the inputs, the outputs, and give them to AND gates and then use them to as inputs. Okay, let's move on. Similarly to the counters that we have seen, which counts from 0, where the count starts from 0 and it goes to all ones, we call them as up counters. We can also have down counters, where the count starts from all ones and then it counts, the numbers are reduced by one number at a time. So for example, if it starts from 15, it reaches to 0 ultimately, and then the backward counting would start again. So kind of like backward counting. If we combine these both operations, we have the type of counter which we call up-down counters. For example, in case of synchronous counters, we can have an up-down counter which has an additional input as up-down, which is active high for up and active low for down. So when this input is high, this counter would work as an up counter. That means the count will start from 000 and it would ultimately reach 111 and then reset. And if we make this input as 0 or low, it would become a down counter, where the count would start from 111 and then 110, 101 and so on till it reaches 000 and then reset to 111. Here are some example waveforms. Initially the counter is set as an up counter by setting the up down input as high, and you can see the output representing the least significant bit, or the output of the first flip-flop has a high frequency, the second flip-flop has a frequency half of the first one, the third one has a frequency 1/4 of the second one, and so on. Once the countdown is activated by activating it by giving it a 0, the waveform changes such that now it starts from 111, and then with each clock pulse the count is reduced by one number. And as an IC, 74HC190 is a high-speed CMOS synchronous up-down counter. It's a decade counter, which means it either counts from 0000 till 1010 or 1001, or it counts from 1001 till 0000 based on whether you are activating as an up counter or a down counter. It also has an active low ripple clock output and a maximum output when the terminal count is reached. Another important thing to remember here is the notation, symbolic notation of a counter. We usually represent a counter by CTR, div, and followed by the number of the count of numbers or the count of sequence which it counts. So for example, a decade counter would be represented as CTR div 10. We use the word div as a divider, since this would divide the frequency of the clock by 10. If it was a binary counter, a 4-bit binary counter, then we would represent it by CTR div 16. If it was a 3-bit counter, then it would be represented as CTR div 8, and so on. A 74HC191 has the same inputs and outputs, but it is a synchronous up-down binary counter. Let's talk about some counter designs. We would need to design a counter, especially if the sequence is not the regular binary sequence that we normally use. So for example, if we can design a counter of any sequence with any order. So for example, we could design a counter where the sequence is not in the binary terms but in the gray code terms. So for example, after 0 0, the next number is 0 1, but the next number is then 1 1 and not 1 0. So a special sequence, if in all the cases where a special sequence is needed, we can apply step-by-step design process. The design process is basically very simple. We just need to know the state table, that is, given a sequence, we need to determine what would be the next sequence. So this kind of table is called a next state table. So for example, if we have a present state of the counter, present output of the counter is 0 0 0 0 0 0 0, the next state is 0 0 1. So we can now just use this as a truth table and use the present state as inputs and the next state is the outputs, and then determine what logic, what combination logic would be needed to get the given output. So we can then implement that. For example, if the output transition is from Q1 to Q1 plus 1, from one flip-flop to the next flip-flop, it is, if the output is changing from 0 to 0, we would need the J to be equal to 0, and K could be anything. It could either be 0 or 1, it doesn't matter. If it's from 0 to 1, then J needs to be 1 and K could be anything again. Similarly for the other two, if the transition is from 1 to 0, the J is X, which means anything. It could either be 0 or 1, it doesn't matter, and K should be 1. Similarly, for if the transition between 1 and 1, from 1 to 1, then J could be anything again, but K should be 0. So based on that, we could then we can easily use a K-map of, for example, for J0 or K0 or any input, and then determine it based on the determine the logic based on this the output. So for example, we have a synchronous counter design here where we have used the gates to get the combinational logic to drive the each individual output based on our design process. We can also use counters in cascade. For example, if you want to use if you want to make a higher order counter, for example, if you want to use a counter which could count from 0 to 255, you could use two 4-bit counters which would make it into an 8-bit counter. In this case, you can see it in this figure. We have two counters, which the first counter divides the frequency by 16, the second counter divides the frequency by 16, so the total frequency division is by 256. So which would make into a counter which could count from 0 to 255, or an 8-bit counter. What the modulus of this cascaded div 16 counters would obviously be 16 times 16 or 256, and if the input frequency is 100 kilohertz, the output frequency would be 100 kilohertz divided by 256, because the frequency is now divided by 256, which is 391 hertz. Counter decoding is used if you want to get a certain number out of the counter. So we could then determine that number. For example, in this given figure, we have used an AND gate as a decoder. and since AND gate would give an output of 1 if all its inputs are high. Its first input for LSB is connected with the Q0 bar, so that means it would be high when Q0 bar is low. Similarly, the second input is connected with Q1 bar, so it would be high if Q1 bar is low, and so on. And the third one is connected to Q2, which would be high if Q2 is high. So that means for Q0, Q1, we need both of the Q0 and Q1 to be high, low, such that Q0 bar and Q1 bar would be high, and so on. So the sequence that it would decode would be 1 0 0, 1 for MSB and 0 0, 0 for the middle bit and 0 for the LSB. So the number decoded by this gate would be Q2, Q1 bar, Q0 bar, or 1 0 0. Okay, so this partial decoding, you can easily understand them by just reading these slides. We can reset a counter with a decoder. For example, whatever sequence that you want to be the terminal sequence and you want to reset the counter, you can use a decoder for that sequence. We have already seen the design of decoders. That is, we could either use AND gates or NAND gates, and we need to make all the inputs of an AND gate high, and only that sequence would be decoded, and that sequence decode could then clear the counters. Okay, this is an example. Okay, so that's the end of this chapter. I hope all the concepts are clear enough. If there are any questions, please feel free to ask. I will be happy to help. And in the next lecture, today or tomorrow, I would discuss about more applications of flip-flops. We would use some registers as well. Thank you very much.